Why does the day have 24 hours? You probably know the answer. Babylonians, base 60 mathematics, ancient Egypt, sundials and water clocks, and a civilization that liked the way the number 12 divided into the night sky. It is settled history, the kind of answer you learnt somewhere, maybe in school, maybe in a documentary you half-watched on a quiet afternoon and it satisfied you. It was the kind of answer that closes a question. A neat box around something that felt large. You will have the full version of that answer in about 20 minutes. The names, the dates, the cuneiform tablets, the way a base 60 number system was passed from hand to hand across 5,000 years until it ended up on your wrist. All of that is coming. It is a beautiful story, and you deserve to hear it told well. But here is the strange thing about that question. If you do not stop at the satisfying answer, if you let it keep going, if you ask the question one more time after you have already heard it answered, it leads somewhere most people never expect. It leads through Babylonian astronomy and Egyptian water clocks and medieval church bells. It leads through railway schedules and the invention of standard time and the slow rotation of a planet you happen to be standing on. It leads through equations written by a man with messy hair in a patent office in Bern. It leads to a letter that man wrote 4 weeks before he died. It leads to the most quietly astonishing thing that physics has ever shown us about the world we live in. And by the end, if you stay with me, you will know something that the Babylonians did not know. Something that Newton did not know. Something that most of the people who have ever asked this question never got to hear the answer to. You will know what the day really is and what it is not, and why it matters that the difference exists. There is no rush. Settle in. Let your shoulders drop. The story we are about to tell stretches across 4,000 years of human attention, across the rotation of a planet, across the structure of space-time itself, and ends in the quiet handwriting of an old man in 1955. We will get there together, slowly, the way these things deserve to be told. So, why does the day have 24 hours? Let us begin. 4,000 years ago, in the flat, fertile land between two rivers, a civilization that we now call the Babylonians looked up at the sky and decided to count it. This is harder than it sounds. The sky is a difficult thing to count. It is mostly empty. The stars are not arranged in any particular order. The moon moves on its own schedule. The sun rises in a slightly different place each morning, drifting north in summer and south in winter, the way a slow tide drifts up and down a shore. If you have ever tried to figure out what the sky is doing from your own backyard, without a clock or a calendar or a planetarium app, you know how strange the experience is. The sky resists being counted. It does not want to give up its rhythm easily. The Babylonians decided to count it anyway. They had certain advantages. They lived on a wide, flat plain where the horizon was clean and the air was often clear. They had a settled civilization with grain surpluses, which meant that some people could spend their time looking up instead of looking down at the soil. They had a written language, which meant that observations made by one person at one time could be passed to another person at another time. And they had something else, something stranger, something that turned out to matter enormously for the rest of human history. They had a number system based on 60. This is the thing that almost no one stops to appreciate. Most number systems through history have been based on 10 because most humans have 10 fingers and most humans count by holding up their hands. 10 is the obvious number. It is the number you arrive at without thinking. The Babylonians used 10 too for small everyday counting. But for serious mathematics, for astronomy, for measuring the things that mattered most, they reached for a different number. they reached for 60. 60 is an extraordinary number. It is what mathematicians call a highly composite number, which is a polite way of saying that it has a lot of friends. 60 divides cleanly by 2. It divides cleanly by 3, by 4, by 5, by 6, by 10, by 12, by 15, by 20, by 30. If you are a farmer trying to split a harvest, or a merchant trying to split a bag of grain, or a builder trying to lay out a foundation, 60 is the number you want. It is the number that almost never leaves you holding an awkward fraction. It is the number that makes the world divide into pieces that fit. The Babylonians took this number and pushed it up into the sky. They divided the circle into 360 degrees. 360 is 6 times 60, which is also the number of days in a year if you round generously, which the Babylonians did. The sky was a great circle. They wanted to mark positions on it, so they laid down the same number system they used for everything else, and the sky received its first numerical grid. From 360 degrees, every other Babylonian astronomical measurement followed. The hour was 60 minutes. The minute was 60 seconds. The day was 12 double hours, with 12 of daylight and 12 of darkness, because 12 too divided cleanly into 60 and into the sky. This is the seed of every clock you have ever looked at. It is the seed of the way you tell time on your phone right now. The reason your phone says 59 and then 60 becomes the next minute, instead of, say, 99 and then 100. The reason an hour is divided into 60 minutes and not into 100. The reason your watch face has 12 marks on it instead of 10. It is all here, in the work of a civilization that lived 4,000 years ago, looking at a sky over a flat green river plain, and reaching for a number system that divided well. The Babylonians did not invent the day. The day had always existed. The earth had always rotated. Light had always come and gone. But they were the first people, as far as we can tell, to take this rotation and pin numbers to it, to make it official, to turn the rising and setting of the sun into a system that other people could use in other places, on other days, and arrive at the same answer. The Egyptians inherited it. They were not far away geographically. Ideas traveled. The Egyptians took the 12 daylight hours and 12 nighttime hours and made them more precise. They built sundials. They built water clocks around 1500 years before the Common Era, give or take. They had standardized the day into 24 divisions, not because 24 was a magical number, because the Babylonians had divided things in 12s, and 12 plus 12 equals 24, and the Egyptians were practical people. The number stuck. From Egypt, the system moved north. It crossed the Mediterranean. It entered Greece. It entered Rome. The Romans were even more practical than the Egyptians, and they had even more reason to standardize. An empire that stretches from Britain to Syria needs people in Britain and people in Syria to know what the third hour of the day means. The Romans took the 24-hour system, used it for their public schedules, used it for their military, used it for their religious observances, and embedded it permanently into the bureaucratic spine of the Western world. When the Roman Empire fell, the system did not. The medieval church inherited it. Monasteries needed to know when to pray. There were 7 canonical prayer times. These had to happen at specific points in the day. Bells rang. Hours were named. The day was a holy thing, and dividing it correctly was a religious obligation, not just a practical one. The number 24 survived in the smoke of churches and the chant of monks, century after century, while almost everything else about the ancient world dissolved. And then, In the 14th century, in a small workshop somewhere in Central Europe, someone built a clock. We do not know exactly who. The early history of mechanical clocks is fragmentary, the way the early history of anything practical and useful tends to be. There were no patents. There were no inventors' biographies. There were quiet craftsmen working in towers, and one day they handed their towns a thing that ticked. The mechanical clock did not look like a modern clock. It often did not even have a face. It just rang bells at the correct times of the day, but it ran on its own. It needed only to be wound. It did not need the sun. This is the moment, more than any other, when the human relationship with time changed permanently. Before the mechanical clock, time was something you read off the sky. You looked up. You estimated. You used the shadow on a sundial, or the level of water in a clock, or the sound of the church bells, which themselves were tied in the end to someone watching the sky. The day was something that happened to you. You moved through it, the way a leaf moves down a stream. Time was a thing the world did, and you were inside it. After the mechanical clock, time was something you read off a machine. The machine did not care about the sky. It ticked. It kept ticking. It kept ticking through the night, through the seasons, through clouds and rain and fog. The hour it announced at noon was the same length as the hour it announced at midnight. This had never been true before. Before, the hour had been a fraction of daylight, and daylight was longer in summer and shorter in winter, and so an hour was a stretchier thing in July than it was in January. The mechanical clock did not stretch. It just ticked. The hour became a fixed quantity. It became a thing in itself, independent of what the sky was doing. This is the moment when the day became a number first and an experience second. From this point forward, time would always pull a little bit away from the world it had been born inside. But the answer to your question is here. In this 1,000-year-long story, the day has 24 hours because the Babylonians liked the number 60, and the Egyptians took their system and split daylight and night each into 12, and the Romans spread it across Europe, and the medieval church preserved it, and the mechanical clock made it permanent. It is an inherited answer. It is a cultural answer. It is the kind of answer that should close the question. It does not, but it should. There is something the inherited answer does not quite resolve. The Babylonians and the Egyptians measured the day. They divided it into 24 hours. But they were measuring something that does not actually behave the way their measurements suggested. The hours they were counting were not all the same length. A summer hour where they lived was longer than a winter hour. Daylight stretched and contracted with the seasons. There were 12 hours of daylight in summer and 12 hours of daylight in winter, but the summer hours were physically longer than the winter hours because daylight itself was longer. Their hour was a fraction of light, not a fixed quantity. This is strange to a modern ear. We think of an hour as a thing, a specific amount. 60 minutes, 3,600 seconds. You can measure an hour. You can put it on a wrist. You can wait an hour and know that exactly an hour has passed. That kind of hour is new. It only really exists from the 14th century onward. Before then, every hour was a soft thing, a seasonal thing, a place-specific thing. The hour you experienced depended on where you were, and when you were, and how you were measuring. Two cities a few hundred miles apart kept slightly different time. Two cities in different countries might use entirely different methods. Even after the mechanical clock, this did not change immediately. The mechanical clock locally fixed the hour. It made all the hours in one city the same length, but it did not synchronize the hours between cities. Each town set its clocks to its own local noon, the moment when the sun crossed directly overhead. If you traveled east, the clocks in the next town read a few minutes later. If you traveled west, they read a few minutes earlier. Every town in Europe, and every town in the Americas, and every town in Asia had its own local time. None of them agreed with each other. They did not need to. People did not travel fast enough for the disagreement to matter. This continued for several centuries. The mechanical clock improved. The pendulum clock arrived. Precision crept upward. Local noons were calculated more carefully. Watches became portable. The wealthy carried personal time in their pockets. But the world itself, the lived experience of moving from one place to another, remained a patchwork of local times that did not quite line up. What changed it was the railway. The railway is one of those inventions that quietly reorganizes everything around it without quite getting credit for the scale of the reorganization. It moves people fast, faster than anyone had ever moved before on land without a horse. A horse can run at 25 or 30 miles an hour for a short distance. A steam train can sustain 40 or 50 or 60 for hours at a time. When you can move that fast, the patchwork of local times stops being a curiosity and becomes an active problem. Imagine you are planning a train schedule. You want trains to leave one city at a specific time, arrive at another city at a specific time, not collide with other trains on the way, and connect with other lines at specific stations. Every town along the route is on its own local time. The town 50 miles east is 3 minutes ahead. The town 100 miles east is 6 minutes ahead. The town 500 miles east is half an hour ahead. None of this is written down anywhere. It is just the way each town happens to set its own clocks. You cannot run a railway like this. You will have crashes. You will have missed connections. You will have engineers waiting in stations for trains that left somewhere else on a different time. The railways began, around the middle of the 19th century, to impose their own standard time on the towns along their routes. The standard time was usually set by the time at the railway's headquarters in a major city, and then it was sent down the line. Every station along the line set its clocks to this railway time, regardless of what the local sun was doing. This was the beginning of standard time. It was not adopted because of any cosmic insight. It was adopted because trains kept missing each other. The next step came in 1884, at a conference in Washington, D.C., when representatives from 26 countries agreed on a single global system of time zones. The world was divided into 24 wedges, each one 15 degrees of longitude wide, each one offset from the next by exactly 1 hour. The prime meridian was drawn through Greenwich, in England, mostly because the British already had a strong claim and a working observatory and the most important navigational charts of the period. Every clock in the world was, from that point onward, calibrated relative to Greenwich. Time zones are 140 years old. This is a stranger fact than it first sounds. The idea that everyone in a given region of the planet should agree on what time it is right now is younger than some of the buildings you have probably visited. It is younger than the telephone. It is younger than the steam engine, which is what forced it into existence. The whole apparatus of synchronized world time, the system that lets you make a phone call to a city on another continent and know exactly what time you are calling them, is barely older than living memory. For most of human history, this was not how time worked. Time was something that happened to you in your specific place, on your specific schedule, with no expectation that someone in another place was experiencing the same moment in the same way. The idea that there is a single shared now, a moment that all humans on Earth can agree on at once, is the cultural product of railway schedules, telegraph wires, and an 1884 conference in Washington. We did not discover time. We invented a system for measuring something we did not fully understand. we agreed collectively to call that system real. And once you start to look at what we agreed to, the agreement starts to come apart. Here is the question we have not really asked yet. 4,000 years into the story, what exactly is the day? You might say, it is the time it takes the Earth to rotate once on its axis. This is a reasonable answer. It is approximately true. It is what most people, if pressed, would say. And it has the virtue of being grounded in something physical, something you could in principle measure, instead of being purely a matter of cultural agreement. But it turns out the Earth does not rotate at a constant rate. This is a small and quiet fact that hides an enormous one. The Earth is not a perfect clock. It wobbles, it speeds up, it slows down. It is affected by the weather, by earthquakes, by the gravitational tug of the moon, by the friction of the tides, by the way ice ages and ice melts redistribute mass across its surface. The day, measured against a sufficiently precise standard, is a slightly different length on different days. It is sometimes a few milliseconds longer. It is sometimes a few milliseconds shorter. Over the long arc of geological time, it is getting reliably and steadily longer, but the day-to-day variations are real and unpredictable. This means that if you build a clock that is more precise than the rotation of the Earth, your clock and the Earth will eventually disagree. Your clock will tick at its fixed rate. The Earth will rotate at its slightly variable rate. After enough time, they will fall out of sync. Your clock will say it is noon. The sun will not be overhead. The sky will quietly disagree with the machine on your wrist. For most of human history, this was not a problem. Our clocks were less precise than the Earth. The Earth was the more reliable standard. We set our clocks to the sky and corrected them whenever they drifted. The Earth was the master. The clock was the apprentice. In the 20th century, this relationship reversed. We built clocks that were better than the Earth. Quartz clocks, which used the regular vibration of a quartz crystal under an electric current, were already more precise than the Earth's rotation by the 1930s. Atomic clocks, which used the regular vibration of atoms themselves, became more precise still by the 1950s. By 1967, the world had officially redefined the second. It was no longer 1/86,400th of an average day. It was 9,192,631,770 oscillations of an atom of cesium 133 at the precise temperature of absolute zero. That is the modern second. It is not a fraction of a day. It is a count of atomic vibrations. Look at what we did when we made this change. We used to measure time by looking at the sky. We used to set our clocks by the position of the sun. We used to derive the second from the rotation of the planet. And then, in 1967, we reversed the direction of measurement. We started measuring the rotation of the planet by looking at how it disagreed with our atomic clocks. We made the atom the master. The Earth became the apprentice. Because the Earth is slowing down. And it is doing so in a way that, if you follow it backward and forward in time, opens up a much larger story than anyone in Babylon could have imagined. The story that is coming is not a story about Babylon. It is not a story about Egypt or Rome or medieval clockmakers or railway schedules. It is a story about the moon and the tides and the slow, patient gravitational pull of one body on another over billions of years, reshaping what a day even is. But before we get there, let your shoulders drop again. Take a slow breath. The Babylonians, the Egyptians, the medieval bells, the mechanical clock in its tower, the railway timetable, the 1884 conference. That is the easy half of the story. The familiar half. the half that any history book will tell you. What comes next is stranger, and it is older than anything humans have ever built. The Earth is slowing down, not by much, not in any way that you would ever notice in a single lifetime, or in 10 lifetimes, or in 1,000 lifetimes. The slowdown is not the kind of thing you can feel. You cannot put your hand on the ground and sense the rotation easing off, the way you might feel a record player slowing as it winds down. The change is too small. It is buried under the noise of weather and wobble and the daily chaos of a planet that does not stand still. But the change is real, and we have measured it, and the measurement is one of the strangest things we know about the world we live on. Every century, the day gets about 1.4 milliseconds longer. That is a tiny number. 1.4 milliseconds is shorter than the time it takes for you to blink, shorter than the time it takes a hummingbird to flap its wings once. You could not measure it with any clock available before the 1950s. You could not feel it. You could not see it. You could not detect it with any instrument that human civilization had ever built until very recently. But if you take that tiny number and you run it backward, the implications become very strange very quickly. 600 million years ago, before there were dinosaurs, before there were really any land animals at all, before the continents were arranged the way you see them on a map, the Earth was still here, still spinning, still orbiting the sun in the same way it does now, but it was spinning faster. The day back then was about 22 hours long. The year was the same length. The Earth made the same trip around the sun, but within that year, it rotated more times because each rotation was shorter. The creatures that lived then, simple, soft-bodied things in shallow seas, lived their lives on a faster planet. The sun rose earlier, the sun set sooner. The cycle of light and dark was tighter and quicker. Run it backward further. 1 billion years ago, the day was perhaps 18 or 19 hours. 2 billion years ago, maybe 14. 4 billion years ago, when the planet was new and the moon was still settling into its orbit and the surface was a hellscape of molten rock and constant impacts, the day may have been as short as 5 or 6 hours. The Earth was spinning like a top. The day raced past. The young Earth lived in a kind of speed-blurred light. And run it forward. 200 million years from now, the day will be 25 hours long. 500 million years from now, perhaps 26 or 27. The slowing continues. It does not stop. The Earth keeps shedding its rotational energy century by century, age by age, into the gravitational pull of the body that orbits it. Because here is the cause of the slowdown. It is not friction with the air. The air is too thin and too irrelevant. It is not the impact of meteors or comets, which are too small to matter. It is not anything about the Earth's interior, although the interior contributes some noise. The cause of the long, slow, geological scale slowdown of the planet you are standing on is, and has always been, the moon. The moon is up there. You have looked at it 1,000 times. You have seen it full, and you have seen it crescent, and you have seen it dark. You have probably never thought of it as a force acting on the planet. It is just a thing in the sky, a pretty round shape against the black, a symbol on flags, a subject for poetry. The moon is 250,000 miles away. It has about 1.5% of the mass of the Earth. It is, by any astronomical standard, a small body. But it is close, and it is gravitationally connected to the planet you are standing on. And that gravitational connection is doing something to the Earth that has been happening since before there was anything alive here to notice. The moon's gravity pulls on the water of the Earth. This is the most direct and obvious of its effects. The water rises slightly on the side of the planet facing the moon, because the moon is pulling that water toward itself. The water also rises on the opposite side, for somewhat more complicated reasons that have to do with the way the moon pulls more strongly on the near side of the Earth than on the far side, leaving the far side, in a sense, behind. The result is two bulges of water, one pointed at the moon, one pointed away from it. These are the tides. You have seen them at any beach you have ever stood on. But the Earth rotates underneath these bulges. The bulges, gravitationally, want to stay pointed at the moon. The Earth, mechanically, wants to keep spinning. The result is that the bulges drag a little. They do not stay perfectly aligned with the moon. They are pulled slightly forward by the rotation of the planet beneath them, and in dragging, they create friction. The water, sloshing across the surface of the Earth as it tries to stay pointed at the moon while the planet keeps turning, rubs against the seafloor, against the continents, against itself. This friction is enormous, cumulative, constant. It has been happening every second of every day for billions of years, and it is doing two things. It is slowing the Earth's rotation, and it is feeding energy back to the moon, which is using that energy to drift slowly away. The moon is moving away from the Earth at a rate of about 1.5 inches per year. This has been measured directly using laser reflectors that astronauts left on the lunar surface during the Apollo missions. We fire a laser at the moon. The light bounces back. We time how long the bounce takes. We do this over and over, year after year. And the time the bounce takes is, very slowly, getting a little longer. The moon is farther away than it used to be. It will keep getting farther, slowly, patiently, 1.5 inches at a time, for billions of years. And as it gets farther, its grip on the Earth weakens slightly, and the slowing of the Earth's rotation slows down too. The system is reaching, very gradually, for a kind of equilibrium. The Earth keeps slowing, the moon keeps drifting, and both of them keep moving toward a future that is so far away it does not really feel like a future at all, more like a place in a story, somewhere you will never go. We will reach that future, eventually, in a moment. But for now, just sit with the dance itself, every second of every day, every season, every year, every century. The tides come in, the tides go out, the bulges drag. The friction releases heat into the oceans and momentum into the moon. The day very slightly gets longer. The moon very slightly gets farther. It has been going on since the moon formed around 4.5 billion years ago in the chaotic young system that we all eventually grew out of. And this is the moon. Only this one moon, doing this to only this one planet. There are larger moons. There are tighter orbits. There are systems where the slowing has gone all the way to the end. We will see one of those next, but for now, the simple fact, the day is getting longer. It has been getting longer the whole time you have been alive. It will keep getting longer for as long as the Earth exists. And the reason is, right there in the sky, in the shape you see on quiet nights when the light is clean, in the soft round body that orbits us at 250,000 miles, the moon is stealing your time, slowly, imperceptibly, permanently, 1 second at a time, over millions of years. And we are giving it away because the laws of physics do not give us any choice. There is a final stage to this process, a place the dance ends. The moon already lives there. The same forces that are slowing the Earth's rotation have already done their work on the moon. Billions of years ago, the moon used to rotate independently. It used to have a moon day, the way the Earth has an Earth day. But the Earth's gravity is much stronger and the moon is much smaller, and the friction worked faster and harder on the smaller body. The moon stopped, or rather, the moon's rotation slowed down until it matched the moon's orbit. The moon now rotates exactly once for every time it orbits the Earth. The result is that the same side of the moon faces the Earth at all times. We see the same face, the same craters, the same dark plains, the same bright highlands, the same gentle pattern that has not changed since human beings first looked up. The far side of the moon was not seen by any human eye until 1959, when a Soviet spacecraft took the first photographs. The moon from where we stand has only ever had one face. This is called tidal locking. It is the natural end state of a gravitational dance between two bodies. Given enough time and enough friction, the smaller body always locks to the larger one. Its rotation matches its orbit. It stops, in a sense, or rather, it falls into a perfectly synchronized loop where it spins exactly fast enough to never quite show its other side. Most of the moons in the solar system are tidally locked to their planets, almost all of them, in fact. The 4 large moons of Jupiter, the moons of Saturn, the moons of Uranus, the moons of Neptune, they all do this. They all keep one face turned toward their parent. They have been doing this since long before life on Earth began. The Earth has not yet caught up. The Earth is still rotating freely, more or less, because the Earth is the larger body in the Earth-Moon system, and the larger body always locks more slowly. The Moon's gravity is weaker. The Earth is bigger. The process is slower, but it is happening. If you let it run all the way out, if you give the system enough time, if you let the tides keep slowing the Earth, and the Moon keep drifting away, and the friction keep doing its quiet, patient work, the Earth will eventually become tidally locked to the Moon. It will rotate exactly once every time the Moon orbits it, which by the time this happens will be a much longer interval than the current month, because the Moon will have drifted much farther away. At that point, a day on Earth will equal a month on Earth. They will be the same thing, the same length, the same number. The question that opened this story, the question about how many hours are in a day, will no longer have a clean answer. The day will have become the month. The Moon will hang in one place in the sky, never moving, visible only from one side of the Earth. The other side will never see it. One face of the planet will always face the Moon. The other face will always face away. This is somewhere around 50 billion years from now. The Sun will have died long before then. The Earth, if it still exists, will be a cold rock orbiting a cold red sun in a much older, much darker universe. The end state of the tidal dance will never be reached. The dance will be interrupted by the death of the system that contains it. But the dance is, mathematically, real. We could trace it forward if we had the patience. It is the natural slow direction of the Earth-Moon relationship, and it is, in its way, one of the most quietly beautiful facts about the world we live on. We are not in a stable system, we are in a slow process. Every day is a different length than every other day. Every century the difference grows. We are in motion. We have always been in motion. The planet is changing, slowly, in ways that almost nothing alive can perceive. This is the fact that begins to undo what the Babylonians thought they had measured. The Babylonians measured a day. The Egyptians measured a day. The medieval church measured a day. They were all measuring slightly different things. The day they measured was a few milliseconds different from the day you live in. The day a dinosaur lived in was an hour shorter than yours. The day a future tidally locked Earth will live in will be 100 times longer than yours. The day is not a thing. The day is a snapshot of a particular moment in the long, slow relationship between a planet and its moon. The Earth is a sloppy clock. The day is a slowly drifting interval. We could not even get a consistent answer to the question, how long is a day, if we asked it across geological time. The day, as a unit, only makes sense if you do not look at it for too long. And so, we built something better. In 1967, the world's measurement authorities, the international body that decides what a meter is, and what a kilogram is, and what a second is, redefined the second. For most of human history, the second had been a fraction of a day. Specifically, 1/86,400th of an average solar day. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. Multiply it out and you get 86,400 seconds in a day. And the second was defined as one of those slices. This definition worked fine as long as the day was a reliable thing to slice. But by 1967, it had become very clear that the day was not reliable. The Earth's rotation was wobbling and slowing in ways that our best clocks could now detect. If we kept defining the second as a slice of a day, the second itself would slowly change length. A second in 1980 would not be the same as a second in 1880. The unit would drift. And a drifting unit is no good for science, for engineering, for the precise work of physics that was, by the 1960s, depending on time measurements at scales the Babylonians could not have imagined. So the world's metrologists, the keepers of measurement, decided to anchor the second to something more reliable than a planet. They anchored it to an atom, specifically to cesium-133. Cesium is a silvery, soft metal, alkaline, the kind of element that reacts violently with water. It sits in the periodic table just below rubidium and just above francium. There is nothing particularly remarkable about cesium chemistry. What is remarkable is its physics, specifically the way its outermost electron behaves when you nudge it with a microwave. When you take an atom of cesium-133 and you put it in just the right kind of microwave radiation, the electron in its outer shell flips between two specific energy states. It oscillates up, down, up, down. The flip happens at an extraordinarily precise frequency. The frequency is, as far as we can measure, exactly the same for every atom of cesium-133. Always, everywhere, in any laboratory, on any planet. It is a property of the atom itself, not of the environment around it. The flip happens 9,192,631,770 times every second. That is the second. It is defined as that many flips of that one specific atom. It is no longer a slice of a day. It is a count of vibrations of an atom in a vacuum chamber. The day, the year, the month, the rotation of the Earth, none of these are involved anymore. The second has been lifted out of the sky and placed inside the quantum mechanical behavior of a single, specific element. Look at what we did when we made this change. We used to measure time by looking at the sky. We used to set our clocks by the position of the sun. We used to derive the second from the rotation of the planet. And then, in 1967, we reversed the direction of measurement. We started measuring the rotation of the planet by looking at how it disagreed with our atomic clocks. We made the atom the master. The Earth became the apprentice. The atom is a better clock than the planet. This is one of the strangest sentences you can write about the universe. A single atom vibrating in a chamber is a more reliable timekeeper than the spinning ball of rock and iron and ocean that you are sitting on. An atomic clock in the best modern designs, will lose or gain less than 1 second every 300 million years. That is, frankly, an absurd level of precision. To put it in perspective, if you started an atomic clock at the time of the dinosaurs, when they were the dominant form of life on Earth, that clock would, today, be off by less than half a second. The dinosaurs went extinct 66 million years ago. Multiply that by 5, and you get the time it would take a modern atomic clock to drift by a single second. The Earth, by comparison, is a mess. The Earth's rotation has noticeable variations on the scale of milliseconds. The Earth slows down after large earthquakes, because earthquakes redistribute mass and change the planet's moment of inertia. The Earth speeds up when ice melts and water flows from the poles toward the equator. The Earth is affected by ocean currents, by atmospheric pressure systems, by the gravitational pull of every other body in the solar system. It is buffeted constantly. It is a clock made of weather and stone, and it shows. If you want to know what time it is, really know. You do not look at the sky. You look at an atom. But here is the strange consequence of this change. We anchored the second to an atom, but we still wanted our clocks to broadly agree with the sun. We still wanted noon to be when the sun was overhead, give or take a small adjustment for time zones. We still wanted the calendar to track the seasons. We did not want our atomic time and our solar time to drift apart over the centuries until the calendar fell out of step with the planet. So we built a correction mechanism. We added a kind of patch. We called it the leap second. A leap second is a second that does not belong to any natural process. It is a second that the world's timekeepers add to atomic time by hand when they decide that atomic time has drifted too far from the rotation of the Earth. They watch the difference between atomic time and astronomical time. When the difference accumulates to about 9/10 of a second, they announce that a leap second will be inserted at the next convenient moment, usually at midnight on June 30th or December 31st, in coordinated universal time. The world's clocks tick 1 extra second. The minute reads 61 seconds long. Then the next minute begins. Time has been quietly adjusted. Since 1972, when the system began, we have added 27 leap seconds, 27 moments that did not happen in nature, that we created, that we inserted into the official record of the world, so that our measurement of time would match the actual rotation of the planet. 27 seconds that do not correspond to any swing of any atom, but to a decision made by a group of metrologists in a building in Paris. Think about what that means. We do not read time, we negotiate it. The official time of the world is a compromise. It is part atomic, part astronomical. It is the product of an ongoing committee discussion about how to reconcile the precision of an atomic vibration with the messiness of a spinning planet. Every leap second is a tiny act of editing the calendar, a small acknowledgement that the universe is not quite as clean as our equations would like. And it is going to get worse, or at least more complicated. There has been serious discussion in the international metrology community about doing away with leap seconds entirely. The argument is that the leap second is disruptive. Computer systems can crash when they encounter a 61-second minute. Time-sensitive engineering has to work around the patches. Some countries want to abandon leap seconds. Others want to keep them. The General Conference on Weights and Measures voted in 2022 to phase out the leap second by 2035 at the earliest. After that, atomic time will drift away from solar time, slowly, century by century, and at some far future point, our calendar will have to be patched in a different way. But for now, The leap second is still with us. Every few years, a new one is announced. Every few years, the world's clocks tick a 61st second. The day, in its official measure, gains a moment. The Earth, in its actual rotation, has fallen slightly behind. We patch the gap. We pretend it never happened. We move on. Stories at the source of human civilization. It is a compromise between atomic precision and planetary mess. It is a system that is, every day, a little less natural and a little more artificial. It is the product of negotiations. The Earth is a terrible clock. We have built a better one, and we use both awkwardly to keep the day going. Most of the time, you do not need to think about this. Your watch is correct enough. Your phone is correct enough. The leap second goes by in the night and you do not notice. But if you do anything that depends on extreme precision, the layers of this system become very real very quickly. The most everyday example is the device in your pocket. Your phone uses time more carefully than almost any other technology in human history. And it does so because of one of the strangest facts about the modern world. It does so because of relativity. You have probably heard of Albert Einstein. You probably have a vague image of him. White hair, mustache, sometimes a tongue stuck out at a camera. He is one of the few scientists in history who became famous in the way that movie stars become famous. His name is shorthand for genius. His face is on posters and t-shirts and the walls of physics classrooms. Most people, if asked, will say he was a great mathematician. He was not, particularly. He was a great physicist. He understood something about the world that no one else had quite understood. And the thing he understood, when you finally see it clearly, is one of the strangest and most beautiful facts about the universe. He worked it out in a single year, 1905. He was 26 years old. He was working as a patent clerk in Bern, Switzerland, evaluating applications for inventions that had been submitted to the Swiss Patent Office. He did this during the day, looking at sketches of devices, deciding whether the claimed inventions were original enough to merit a patent. In the evenings, after work, he did physics. He had a small group of friends he talked to. He published almost nothing. He was, by any conventional measure, a minor figure in the world of science. 1905 is sometimes called the miracle year. In a span of a few months, Einstein published 4 papers that, taken together, fundamentally changed our understanding of reality. One of them was on the photoelectric effect, which would later win him the Nobel Prize and help launch quantum mechanics. One was on Brownian motion, which proved the existence of atoms. One was a short follow-up that introduced the equation that would become his most famous, the one about energy and mass. The 4th paper was on what he called the electrodynamics of moving bodies. It is the paper that gave us special relativity. The idea at its core is very simple. Simple enough that it can be stated in a single sentence. The speed of light is the same for everyone. This sounds harmless. It does not sound like a sentence that should reshape your understanding of the universe. It sounds like the kind of fact you might find in a physics textbook, a passing observation, a unit you should remember. The speed of light in a vacuum is approximately 299,792,458 meters per second. Fine. Big number. Let us move on. But pause for a moment. Think about what the sentence actually claims. It claims that no matter how fast you are moving, when you measure the speed of light, you will get the same answer. If you are standing still on a platform and light flashes past you, you measure 299 million meters per second. If you are on a train traveling at half the speed of light and the same light flashes past you, you measure the same number, 299 million meters per second. The light is not faster from your point of view because you are moving alongside it, and it is not slower because the train you are on is racing in the same direction. It is exactly the same speed. From every observer's point of view, in every reference frame, light always moves at the same speed. This violates everything you know about how speeds work. If you are on a train moving at 50 miles an hour and you throw a ball forward at 20 miles an hour, an observer on the ground sees the ball moving at 70 miles an hour. Speeds add. This is obvious. This is how the world works. This is why a car can drive faster than a person can run. You add the speed of your legs to the speed of the car, and you go faster than you could go alone. But light does not add. Light is fixed. Light is the same speed for everyone in every reference frame, regardless of how they are moving. The only way this can be true is if something else gives. The only way two observers, one stationary and one moving, can both measure light traveling at the same speed is if their measurements of the things that go into speed, which are distance and time, are different. If they disagree on how far the light traveled, or on how long it took to get there, or both, then they can still arrive at the same final answer for its speed. Einstein worked out the math. He showed that this is exactly what happens. When you move, your measurements of distance and time change. The faster you move, the more they change. Distances contract. Time stretches. The faster you go, the more pronounced both effects become. Until at the speed of light itself, time stops entirely and distances in your direction of motion collapse to zero. This is the consequence of the single, simple sentence about the speed of light. Time itself is not a fixed thing. Time depends on motion. Two people moving at different speeds experience time at different rates. Their clocks, if compared, will not agree. And neither one of them is wrong. Both of them are correct. Their clocks are measuring real time, just real time, as experienced by their particular reference frame. We have tested this many times, in many ways, with many different kinds of experiments. The first really clean test was in 1971, when two physicists named Hafeley and Keating took 4 cesium atomic clocks and flew them around the world twice, once eastward, once westward. They compared the clocks afterward to identical clocks that had stayed on the ground. The flown clocks were off. The eastward clocks, which had moved faster relative to the rotating Earth, ran slightly slower than the ground clocks. The westward clocks, which moved slower relative to the rotating Earth, ran slightly faster. The differences were tiny, tens of nanoseconds. But they matched Einstein's predictions exactly. Time itself had been measured to flow at different rates for clocks that moved at different speeds. The experiment had been done. The numbers had come out as predicted. You are not aging at the same rate as the person next to you. If they have walked across the room while you stayed still, they have aged very slightly slower than you. If they have driven to the grocery store while you stayed home, they have come back very slightly younger than they would have otherwise been. If they have flown across the country, the effect is larger, though still imperceptibly small. The difference between you and them in raw seconds is so tiny that no clock you own could measure it. But it is real. It is a real difference in the amount of time each of you has experienced. You are on slightly different timelines. You have always been on slightly different timelines. Every motion, every step, every breath that moves your body through space changes the rate at which you are aging. This is not a metaphor. It is the actual structure of the universe. If you push the effect further, it becomes more dramatic. If you could travel close to the speed of light, the differences would become enormous. A round trip to a nearby star at 99% of the speed of light might take you a few years by your own clock. But by the clock of the people you left behind on Earth, decades would have passed. You would come home younger than your siblings, younger than the friends you had said goodbye to, younger, perhaps, than your own children. The faster you move, the more time stretches. This is the twin paradox. It is not actually a paradox, just a counterintuitive consequence. If you have two twins, and one stays on Earth while the other gets on a fast spaceship and flies away, when the traveling twin comes back, they will be physically younger than the twin who stayed home. Their cells will have divided fewer times. Their hair will have grown less. They will have eaten fewer meals. They will not have lived as much life. By any biological measure you care to use, they will be younger than their sibling. And the difference will be permanent. It will not fade. It will not balance out. It is a real difference in time experienced. The slower of the two will not feel anything strange. Neither will the faster. Each will experience time at the normal rate, from their own perspective. It is only when they meet again, when they compare their clocks, that the difference becomes visible. They have aged differently because they have moved differently. There is no universal clock running in the background. There is only the time each of them experienced in their own reference frame. This is the first place where the idea of a shared now begins to come apart. If your aging depends on your motion, if everyone's aging depends on their motion, if every object in the universe is moving relative to every other object in some way, then no two objects in the universe are aging at exactly the same rate. Every star is on its own timeline. Every planet is on its own timeline. Every person is on their own timeline. Every atom is on its own timeline. The differences are mostly small, mostly imperceptible, but they are real, and they accumulate. There is no universal tick, no cosmic metronome, no single clock that the whole universe is synchronized to. Each of us is on our own timeline. We have always been on our own timeline. We always will be. And this is just the first piece of what relativity reveals. Because in 1905, Einstein had not yet tackled the bigger question. He had not yet asked what gravity does to time. He had not yet realized that mass itself bends space-time, and that the bending changes how time flows. That was the next paper. That was the next 10 years of work. That was the second great revolution he was about to bring. It took Einstein another decade to work out what gravity does to time. Special relativity, the 1905 paper, was about motion. But Einstein knew, almost immediately, that the theory was incomplete. It described how time behaved for things moving at different speeds. It did not describe what happened when those things were also being pulled on by gravity. And gravity, in his view, was where the real story was hiding. He worked on it for 10 years. He learned mathematics he had not known. He recruited collaborators. He went down false paths and came back. He made the leap, partway through, from working as a patent clerk to working as a professor. By 1915, he had the answer. He called it general relativity, and it changed everything again. The core idea of general relativity is also surprisingly simple. It is that gravity is not really a force the way Newton had described it. Gravity is geometry. Mass bends the shape of space-time. Other objects move through that bent shape. What we call gravitational attraction is just the natural straight-line motion of objects through a space that has been curved by mass. This sounds abstract. It is hard to picture. The usual analogy is a rubber sheet stretched flat, with a bowling ball placed in the middle. The bowling ball makes a dip in the sheet. If you roll a marble across the sheet, the marble will curve toward the bowling ball, not because the bowling ball is pulling on the marble, but because the marble is following the curvature of the sheet. The marble is moving in a straight line, as far as the marble is concerned. It is just that the sheet itself is not flat anymore. This is a two-dimensional version of what gravity actually does in our four-dimensional space-time. Mass curves the geometry. Objects move through the curved geometry. The motion looks like attraction, but it is really just inertia following the shape of the space. The consequence for time is profound. In general relativity, the curvature of space-time is not just a curvature of space. It is a curvature of time, too. The two are joined. Where space is curved, time is curved. Where there is more mass, there is more curvature. And the more curvature, the slower time runs. This means that clocks at different heights in a gravitational field run at different rates. A clock on the ground, deep in the gravitational well of the Earth, runs slightly slower than a clock on top of a mountain, which is slightly farther from the Earth's center. The difference is tiny, far below anything you could feel or see in daily life, but it is real, and it has been measured directly. You can put two atomic clocks at different altitudes, leave them there for long enough, and compare them afterward. The higher clock will have ticked slightly more times. The lower clock will have ticked slightly fewer. Time itself has run at different rates at the two heights. The difference between the basement and the attic of your house is real. The clock in your basement is, at this very moment, running slower than the clock in your attic. The difference is too small to measure with anything in your house, but it is real, and it has been confirmed by experiment. The lower you are, the slower time flows. The closer to a massive object, the deeper into the gravitational well, the more sluggish the seconds become. This effect becomes much larger near very massive objects. Near a black hole where the gravitational field is extreme, time slows dramatically compared to far away. If you could watch someone fall toward a black hole from a safe distance, you would see their clock run slower and slower as they approached the event horizon. They would seem to fall in slow motion. Their watch would tick more and more slowly. At the event horizon itself, from your perspective, time would appear to stop entirely. The falling person would seem to freeze, hanging there, never quite crossing the boundary. From their own perspective, of course, nothing strange would happen. Their watch would tick at the normal rate. They would feel themselves falling. They would cross the event horizon at the regular pace. They would experience time as they always had. But the watcher outside would see them, in some sense, never arrive. Their fall would slow and approach an asymptote that they never quite reach. The black hole would absorb them eventually in their own time. But from outside, the moment of crossing would be invisible. It would be lost in the slowing of clocks. This is real physics. It is not science fiction. It is what general relativity predicts and what observations confirm. Time is not a uniform thing across the universe. It speeds up and slows down depending on where you are in the gravitational field. Two people standing in different parts of the same room are experiencing slightly different rates of time. Two people on different planets are experiencing more different rates. Two people, one of them near a black hole, would be on radically different timelines. The most everyday consequence of this is in the device you almost certainly own, your phone. Your phone uses the Global Positioning System, or GPS, to determine where you are. GPS works by triangulating signals from a fleet of satellites orbiting the Earth. The satellites broadcast the exact time they sent each signal. Your phone receives the signals and measures how long they took to arrive. From the time delays, your phone calculates how far away each satellite is. From the distances to multiple satellites, your phone calculates its own position on the surface of the Earth. For this to work, the clocks on the GPS satellites have to be extraordinarily precise. They have to agree to within a few billionths of a second with the clocks on the ground. If they did not, the position calculations would be wildly wrong. And here is the thing. The clocks on the GPS satellites do not agree with the clocks on the ground. They cannot. They are in a different gravitational field. They are at a much higher altitude, about 20,000 kilometers above the surface of the Earth, where gravity is weaker. According to general relativity, they should tick faster than ground clocks. According to special relativity, they should tick slower because they are orbiting at high speed. The two effects work in opposite directions, but they do not cancel out. The general relativity effect is larger. The net result is that the GPS satellite clocks tick faster than ground clocks by about 38 microseconds per day. 38 microseconds is a tiny amount. But 38 microseconds per day, accumulated over even a few hours, is enough to make the GPS system useless. The satellites broadcast their time. The phone uses that time to calculate distance. If the time is wrong by 38 microseconds, the distance calculation is wrong by about 11 kilometers. Your phone would tell you that you were standing in the wrong city. GPS satellites have a relativistic correction built into their clocks. They are deliberately set to tick slightly slower than the natural rate, so that the relativistic speedup brings them into agreement with ground clocks. Without this correction, GPS would not work. Without Einstein's theory, the navigation app on your phone would be telling you to take a left turn into a cornfield 10 kilometers from where you actually are. You depend on relativity every day. Every time you check a map. Every time your car follows a directions app. Every time you find your way to a place you have never been before. The mathematical structure that Einstein worked out in 1915, the geometry of curved spacetime, and the slowing of time in gravitational fields is built into the firmware of the satellites overhead, quietly correcting for the differences between your time and theirs. This is the most practical consequence of one of the strangest facts in physics. Time is not universal. Two clocks in two places are not synchronized. The difference between them is small, but it is real, and modern civilization, in its smallest details, has had to account for it. There is one last piece of this that we need to look at. It is the deepest and the strangest, but it follows naturally from the others, and once you see it, the picture of time we have been building starts to take a final shape. The piece is called the relativity of simultaneity. It is the idea that two events that appear to happen at the same moment for one observer may appear to happen at different moments for another observer, and there is no way from any external perspective to decide which observer is correct. Einstein illustrated this with a famous thought experiment involving a train. Imagine a long train moving at high speed past a platform. There is an observer standing on the platform watching the train go by. There is another observer riding on the train, standing in the middle of one of the cars. At the moment, the two observers are aligned with each other. Lightning strikes both ends of the train at once. Two flashes, one at the front, one at the back. From the platform observer's perspective, the two strikes happen at the same instant. They see both flashes at the same time. The strikes were simultaneous. But what does the train observer see? The train observer is moving. They are moving toward the front of the train and away from the back. The light from the front strike is racing toward them. The light from the back strike is also racing toward them, but they are moving away from it. The light from the front reaches the train observer first. The light from the back reaches them slightly later. Now, both observers have to agree that the speed of light is the same in all reference frames. That is the foundation of all of this. So the train observer cannot just say that the light from the back was slower. They have to conclude something stranger. They have to conclude that the front strike actually happened first. From their perspective, on the train, the events were not simultaneous. The front strike happened, and then the back strike happened. They are sure of this, because the light from the front reached them before the light from the back. The platform observer is also sure. From their perspective, the two strikes happened at the same moment. They saw both flashes at the same time. So who is right? This is the surprise. They are both right. Each is correctly observing what happened in their own reference frame. The events themselves do not have a single correct order. The order depends on who is watching. There is no privileged perspective. There is no fact of the matter outside of any specific observer's frame about which event happened first. This is not a quirk of perception. It is not a delay effect. It is the actual structure of space-time. Two events that are separated by space and not connected by a signal that travels at or below the speed of light do not have a fixed temporal order. Different observers, moving at different speeds, will disagree on which one came first, and there is no way to settle the disagreement. What does this mean for the idea of a shared present moment? It means there is no shared present moment. Not really. Not in the way we usually imagine it. Right now, at this instant, there is no fact of the matter about what is happening on a distant planet or in another galaxy or in any other part of the universe outside your immediate vicinity. There is your present, here where you are, in your particular reference frame. And there are other observers in other reference frames with their own presence. None of these presents are exactly aligned. None of them agree on what is happening everywhere else at once. The notion of a universal now, a single moment of time that stretches across the whole universe, a global slice of right this second that we all share, does not exist in relativity. It is a useful approximation in daily life when everyone is moving slowly compared to the speed of light. But as a fundamental description of reality, it is wrong. The universe is not arranged that way. There is no global now. This is hard to feel. It does not match our intuition. We feel every moment that something is happening right now, that this is the moment of the present, that the present is a real thing, a thin slice of time that we are passing through. We feel that distant events are also happening right now, even if we cannot see them yet. We feel that there is a fact about what is happening on the other side of the galaxy at this very instant, even if we cannot know it. Relativity says, no. There is no fact. There is your present in your reference frame. And there are other presents in other reference frames. The presents do not align. The universe does not have a single time. It has a four-dimensional structure, and the slices we call the present are slices we choose, not slices the universe itself provides. We have been measuring time. We started with Babylonians counting sky degrees and ended with Einstein observing trains. We started with a number system and ended with the realization that the number itself depends on who is counting. We started with the day. We have ended with a structure of reality in which the day, the moment, the present, all of these familiar things are not what they seemed. What is left then? If now is not a universal fact, if every observer has their own time, If motion changes the rate of clocks and gravity changes them differently, what is time? Einstein had a way of answering that question. He gave the answer in many places. In equations, in lectures, in conversations with friends. But the most beautiful and most direct expression of his view came in a letter he wrote, very near the end of his life, to the family of his oldest friend. That letter is where we are going next. In the early months of 1955, a man named Michel Bessot died. Michel Bessot was not famous. He was an engineer, born in Italy, who had spent most of his career in Switzerland, working in patent offices and consulting firms. He had no particular accomplishments that history records. He was a quiet, thoughtful man. He had married well. He had a son. He had lived a normal, decent, unremarkable life. But Michel Bessot was Albert Einstein's oldest friend. They had met in Zurich in the 1890s, when both of them were young men studying at the Polytechnic. They had become friends almost immediately. They had stayed friends for 60 years. When Einstein was working out special relativity, in his evenings after his patent office shifts, it was Michel Bessot he talked to. Bessot was the only person, by name, that Einstein thanked in his 1905 paper on the electrodynamics of moving bodies. Across decades, across an ocean, through wars and migrations and the upheavals of 2 world wars, the two men had kept writing letters to each other. They had talked about physics. They had talked about philosophy. They had talked about politics and books and their families. They had been, in a quiet, steady way, the closest of friends. When Bessot died in 1955 in Geneva, his son wrote to Einstein in Princeton to share the news. Einstein wrote back. The letter is short. It is in German, written in Einstein's looping handwriting. It is now in the archives, and you can see images of it online if you want to. It is one of the most extraordinary documents in the history of human thought. And it was written, in its original moment, simply as a letter of condolence. As an old man writing to the family of a friend, sharing his grief and his hope. In the letter, Einstein wrote, and I will translate the relevant lines carefully. Now he has gone a little ahead of me, departing from this strange world. This means nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. Stop and read that sentence again. Read it slowly. Let the words settle. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. This is the man who worked out special relativity, the man who worked out general relativity, the man who, more than any other single person, understood the structure of time at a level no one had ever understood before. And in the last letter he wrote about the death of his closest friend, he said this: the distinction between past, present, and future is an illusion. A persistent one, yes. A stubborn one, but still an illusion. Einstein died 4 weeks later. He never retracted the statement. He never softened it. He never wrote, as a follow-up, that he had been speaking poetically or had been trying to comfort the grieving family with metaphor. He meant it. As far as the historical record shows, this is what he believed about the nature of time at the very end of his life, having spent 50 years thinking carefully about exactly that question. What did he mean by it? The answer is in the geometry of spacetime that he himself had worked out. Relativity does not just say that time is relative to motion and to gravity. It says that time is part of a larger geometric structure called spacetime, in which the past, the present, and the future all exist as a single four-dimensional shape. The shape does not change, it just is. The flow of time, the sensation of one moment passing into the next, is not described anywhere in the geometry. The geometry contains all of time at once, laid out as a complete static structure, with every moment of every life existing at its own coordinate, neither created nor destroyed by the passing of any other moment. This view of time has a name. It is called the block universe. Sometimes it is called eternalism. It is the view that all moments, past, present, and future, exist equally, all at once, in the four-dimensional manifold of space-time. The present is not a special moment. It is just the moment you happen to be in. The past is not gone. It is just elsewhere, at its own coordinate. The future is not unmade. It already exists. It is simply not yet where you are. This is what Einstein meant in his letter. He was telling Besso's family gently that in the deepest physical sense, their father was not gone. He had simply preceded them slightly along a coordinate axis. His existence was still there, at the location it had always occupied. The moments he had lived were still located in space-time, at the points where they had occurred. They had not vanished. They had just become inaccessible to him by his ordinary forward motion through time. He has gone a little ahead of me, preceded me, not erased, just at a different point in the four-dimensional structure that contains all of us. This is one of the strangest and most beautiful ideas in physics. And it is not a wild speculation. It is the natural consequence of the equations Einstein himself had written. It is what the math says when you read it carefully. The equations of relativity describe space-time as a four-dimensional manifold. They do not single out any moment as the present. They do not give any direction to time. The flow of time, the experience of now passing into then, is something we add on top of the geometry. It is a feature of our minds. It is not a feature of the geometry itself. There is a quote from a more recent physicist, the Italian Carlo Rovelli, who has written beautifully about this. He says, in his book on the nature of time, "The flow of time is not a feature of reality, it is a feature of our ignorance." What he means is that the universe does not flow, the universe is. It exists as a four-dimensional structure all at once, in the way that a sculpture exists all at once, even though you can only see one side of it from any given angle. Our experience of the flow of time is a consequence of our limited perspective. We can only access the universe at one coordinate at a time. We move forward through that coordinate. We remember the coordinates we have already passed through. We anticipate the coordinates we have not yet reached. But the coordinates themselves are all there all the time. The universe is not flowing. We are, in a sense, sliding along inside something that itself does not move. Not every physicist agrees with this view. There are physicists, perhaps most prominently Lee Smolin, who think that the block universe is wrong, that time is genuinely flowing, that the present moment is real, that the future is genuinely open and unmade. The argument is unresolved. The mathematics of relativity does not by itself decide the issue. You can interpret the same equations in either way, depending on philosophical preferences and on what kinds of additional principles you think reality should obey. But the block universe is the most natural reading of the equations Einstein gave us. It is what the math, taken at face value, seems to be saying. And it is what Einstein himself, judging from his letter to Besso's family, appears to have believed. If he was right, the implications are extraordinary. Let us try to picture it, even though it is hard. You have probably seen a movie reel, the old kind, the kind that came on a spool of film before everything became digital. A movie reel is a long strip of frames. Each frame is a single picture. When the reel is played through a projector, the frames pass by one at a time, 24 per second, fast enough that they appear to flow into one another, fast enough that they look like motion. But the motion is not really there. The film is not moving. The frames are static. The motion is something the projector creates by passing through the frames in order. A block universe is something like that, only in 4 dimensions instead of 1. Imagine that the entire history of the universe, from the beginning to the end, is a 4-dimensional structure. 3 dimensions of space, 1 dimension of time. Every event that has ever happened or will ever happen exists at some specific point in this structure. The point has 3 spatial coordinates telling you where the event happened, and 1 temporal coordinate telling you when. The Big Bang is at one end. The heat death of the universe, if that is how things end, is at the other. Every other event, every moment of every life, every star that has burned, every galaxy that has formed, every breath you have ever taken, sits at its own point in this great 4-dimensional shape. The shape does not move. The shape just is. You, as a living being, are not a single point in this shape. You are a long, worm-like extension, a curve through space-time that begins at the point of your birth and ends at the point of your death. Your world line. Every other living being is the same. Your friends are world lines. Your family is world lines. The Earth is a world line. The Sun is a world line. The galaxy is a world line. Everything that exists as an extended shape in the 4-dimensional manifold. Your experience of moving through time is something like a flashlight beam moving along your own world line. At each instant, you are illuminating a single point along it. You call that point now. A second later, the beam has moved a little further. You call that new point now, and the previous one becomes the moment before. But the previous moment is still there. It has not gone anywhere. The shape is unchanged. Only the position of your beam has shifted. This means that the past is still there. Every moment you have ever lived is still there, fixed in the geometry of space-time. The moment you took your first breath, the moment you learned to walk, the moment you fell in love for the first time, the moment you said goodbye to someone you loved. All of these moments are still there. They are still real. They are still located at their coordinates. They are just no longer where your flashlight beam is shining. It also means the future is there. Every moment you have not yet lived is already there too, fixed at its own coordinate in the structure. The flashlight beam has not yet reached those moments, but they exist, in some sense, in the same way the past exists. The shape is complete. The block is whole. This is, if you take it seriously, one of the most strange and beautiful and quietly unsettling ideas that physics has ever produced. It is also, on a quiet night, when you are warm and safe and lying in bed and the world around you is very still, one of the most peaceful things you can think about. Because if the block universe is correct, then nothing that has ever happened is gone. Every moment you have ever loved is still there. Every face you have ever cared about, every laugh, every quiet, warm afternoon, every meal eaten with people who are no longer with you, every kindness offered to you, every kindness you offered to someone else, all of these are still real. They are still located somewhere in the 4-dimensional structure. They are not erased, they are not destroyed, they are simply not where you are anymore. You cannot return to them. The flashlight beam does not move backward. You only get to illuminate one direction along your world line. But the moments are not gone. They are simply elsewhere. There is a peace in this, if you let yourself feel it. The people who came before you, the people you have lost, the years that have passed, are not deleted from the universe. They are not gone in the way we usually imagine. They are at their coordinates. They are where they always were. The universe, in its full four-dimensional structure, still contains them. It always will. Einstein wrote his letter to the Besso family for this reason, I think. He was not trying to deny grief. He was not pretending that loss was not real. He understood loss. He had outlived many people he loved. But he was also a physicist, and what he had spent his life learning was that time was not what people commonly thought it was. The distinction between past and present, the sharp line we draw between what is and what was, is not what the equations show. The equations show a single static four-dimensional structure, with every moment existing at its place. His friend was not gone. He was simply at his location. He had preceded Einstein slightly along the coordinate. That was all. This is what the math says, taken at its most natural reading. It is also, of course, very strange, and you do not have to fully accept it to feel something soft and good about the idea. You can hold it lightly, you can let it sit, you can let your shoulders drop a little further into the bed or the chair or the floor where you happen to be lying, and let the idea exist in your mind for a moment without grabbing too hard at it. The universe might be a block. Every moment might be permanent. Time might not be a river, but a long, calm landscape. You do not have to decide tonight. The thought is simply there, like a stone you have picked up and turned over in your hand. If all moments exist equally in the block universe, then why does time feel like it moves forward? Why do we remember the past and not the future? Why do causes precede effects? Why does an egg break and not unbreak? Why does coffee cool and never spontaneously heat itself up again? The answer to all of these questions has a single source, and it is one of the deepest principles in physics. It is called the second law of thermodynamics, and it tells us why we experience time the way we do, even if the underlying geometry of reality does not flow. The second law of thermodynamics says that the entropy of an isolated system always increases. Entropy is roughly a measure of disorder. A neatly stacked pile of books has low entropy. A scattered jumble of books has high entropy. Heat flowing from hot to cold increases entropy. Heat flowing from cold to hot would decrease it, and that is why we never see heat flow that way. The universe as a whole is steadily moving from lower entropy states to higher entropy states. Disorder grows. Things break down. Useful energy becomes useless energy. The arrow points one way and one way only. The laws of physics, at the level of the equations, do not really distinguish between past and future. Most of the equations are time-symmetric. If you ran the universe backward, the equations would still work. A movie played in reverse would look strange, but it would not violate the fundamental laws of motion. Atoms moving backward, planets orbiting backward, light traveling backward. All of this is mathematically consistent with the basic laws. The basic laws do not care about direction in time. The exception is the second law, the increase of entropy. This is the one thing in physics that has a clear direction. It is the reason we know time goes forward, because we can see entropy increasing. The clean room becomes dirty. The hot tea becomes cool. The young face becomes old. Everywhere we look, things move from more ordered to less ordered states. The arrow of time, the reason we experience time as flowing, comes from this. Not from anything fundamental in the geometry of space-time, from the statistical fact that disorder is more probable than order, and so things drift toward disorder over time. Why is there entropy at all? Why did the universe start in a low entropy state so that it had somewhere to go? This is one of the deep questions in cosmology, and the honest answer is that we are not sure. The Big Bang was an extraordinarily low entropy state. The universe began in an incredibly ordered configuration, and it has been spreading out, cooling down, and growing more disordered ever since. Why the universe started that way is, in some sense, a question physics has not yet answered. It just did. But given that it did, the rest follows. Entropy increases. Things move from order to disorder. And living beings like us, who are made of ordered structures, who maintain ourselves as low entropy patterns in a high entropy environment, experience the increase as the flow of time. We remember the past because the past is the more ordered state that we came from. We anticipate the future because the future is the less ordered state we are heading toward. The asymmetry between memory and anticipation, the asymmetry between cause and effect, the asymmetry that makes the world feel directional, all of this comes from entropy. You experience time because you are the wreckage of the Big Bang. You are a structure of order, slowly dissolving back into disorder. The flow of time you feel is the slow, steady dissolution of the order you were born with. Your cells will divide for a while, then they will stop. Your memories will accumulate for a while, then they will begin to fade. The order you maintain by eating and breathing and sleeping and healing will, eventually, drop below the threshold needed to sustain you, and you will return to the larger flow of entropy from which you came. This is not sad. It is not a punishment. It is the natural shape of being a temporary, low-entropy configuration in an expanding universe that is moving slowly toward equilibrium. The flow of time you experience is the local feeling of being part of this larger flow, and the equations do not capture this. The equations of physics, the deep ones, are silent on the matter. They describe the structure of space-time. They describe the curvature, the geodesics, the masses, the energies. They do not describe the flow. The flow is something that emerges statistically from the fact that we live in a universe that started low entropy and is moving toward high entropy. The arrow is a thermodynamic arrow. It is not a fundamental arrow. This is the deepest sense in which the present moment is not a feature of the universe. The universe has a structure. The structure has a beginning, low in entropy, and an end, high in entropy. The structure does not have a present. The present is what we feel when we are partway between the beginning and the end, oriented in such a way that we can remember in one direction and anticipate in the other. Other observers, other beings, even other versions of ourselves at other coordinates are all having their own present moments. None of them is more real than any other. They are all just where each of those observers happens to be. The day, the hour, the second, the present, the past, the future. We have unwound all of them, gently, one at a time. We started with Babylonians and base 60 mathematics, and we have ended with a vision of the universe as a static four-dimensional block in which all moments coexist, with the flow of time being a local feeling produced by the increase of entropy. The day has 24 hours because humans decided it should, but the day itself, as a fundamental piece of the world, is something looser, stranger, and more wonderful than we tend to assume. You are still warm and safe, wherever you are. The moments you have loved are still real. The people you have lost are still located in the structure of space-time. The flow of time you feel is the soft, slow process of your local order dissolving into the larger sea. And the equations, beneath all of this, hum quietly along, describing a universe that does not move, that simply is, with all of its moments equally present and all of its losses equally preserved. This is the place where physics arrives. Not at a fact exactly, at a vision, at a way of seeing, at a kind of patience with what is, because what is, in its deepest structure, is already all of it, all at once. If the past is still there, fixed at its coordinates in space-time, what is your memory of it? Memory feels, on a surface level, like a kind of recording. You experience an event, you store it, later you recall it. The recall feels like a replay. You re-see the room, re-hear the voice, re-feel the warmth of the moment. The memory feels like a copy of the original event, slightly faded perhaps, slightly blurred, but recognizably the same thing. We talk about memories as if they were photographs or videos. We describe ourselves as remembering, as if we had a small library of recordings inside our heads, and we were going to find one and play it. This is not how memory works. The neuroscience of memory, as best as we currently understand it, is that memory is reconstructive, not archival. You do not store an experience and replay it. You store fragments. You store patterns of activation across networks of neurons. When you remember, you do not retrieve the original experience. You rebuild it. Your brain takes the stored fragments and assembles them into something coherent, filling in the gaps as it goes. The memory you experience is a current construction, not a retrieved recording. This has consequences that surprise most people when they first hear about them. Every time you remember an event, you slightly change the memory of it. The act of remembering rewrites what is stored. Each recall introduces small alterations. After enough recalls, the memory may bear only a loose resemblance to what actually happened. You may remember things that did not occur. You may forget things that did. You may shift the timing, change the colors, edit the dialogue, all without realizing. In the block universe view, the actual event still exists at its coordinate in space-time. The afternoon you remember, the conversation you had, the face of the person you loved, all of these are still located in the four-dimensional structure exactly as they were. They have not changed. They cannot change. They are at their coordinates. They will always have been there, but your access to them is indirect. You do not have a window into the past. You have a reconstruction made by your current brain. The reconstruction is approximate. It is partial. It is shaped by everything that has happened to you since. This means something gentle and a little surprising. The person you remember is not exactly the person who existed at the coordinate you are remembering. The memory you have of your mother as she was 20 years ago is not the same as the actual moment 20 years ago. The real moment is still there, fixed, complete, holding all the details you have forgotten and many you never noticed at the time. Your memory is a model of it, a model made of neurons, a model that has been edited and re-edited every time you have called it up. In some ways, this means the past is more present than memory suggests. It is still there in the structure of space-time. The full reality of every moment is preserved at its coordinate. The moments themselves are not the faded versions you carry. They are the full, original moments, complete and unaltered. In other ways, this means the past is less accessible than memory suggests. You do not have the moments themselves. You only have your current reconstructions of them. The moments are real, but you cannot reach them. You have only the model. This is, in a way, a description of how being alive feels. You are always a little distance away from what has happened to you. You are always working with reconstructions. The actual events are real, somewhere at their coordinates. But you experience them through layers of your own neural processing, through the years of your own changing brain, through the filters of what you have come to believe about yourself and about your life. The past is more permanent than you usually feel, and less reachable than you usually believe. Both of these things are true at once. There is a particular kind of grief that comes from believing the past is gone. The feeling that the people you have lost are simply not there anymore, that the years you lived with them are erased, that the warmth of those rooms, those afternoons, those conversations has been taken from the world. The block universe offers a different way to hold this. The people are not gone. The moments are not erased. The afternoons you lived through are still located in space-time at the coordinates where they occurred. The warmth was real. The conversations were real. The years happened. They will always have happened. The universe, in its four-dimensional structure, still contains them. This is not the same as saying the people are still alive, in the sense you usually mean alive. They are not at your current coordinate. You cannot reach them by walking across a room. You cannot reach them by waiting. You will not encounter them again in your forward motion through your own world line. In that ordinary sense, they are gone, but they are not erased. Einstein, in his letter, used the word preceded. To precede is to go before, to walk in front, to arrive at a place slightly earlier. It does not mean to vanish. It means to be at a different place along the path. Your friend is still on the path. They have simply gotten to their final coordinate a little sooner than you will get to yours. This is not comfort in the conventional sense. It does not bring anyone back. It does not let you talk to them again. It does not change the fact that you are alone in your forward motion on this particular stretch of your world line. The grief is real. The absence is real. The loss is real in every way that matters to your life as you live it. But there is a peace in this that you can find if you look for it. The peace of seeing the structure clearly and recognizing that nothing in it can be taken away. Everything that has happened has happened. It will always have happened. The moment is fixed. The loss is, in the deepest physical sense, impossible. You will lose people. You have already lost people. You will lose more. This is part of being a low-entropy structure in a high-entropy universe, part of the long, slow process of dissolution that is being alive. But what you have shared with the people you have loved is preserved in the geometry. It is at its coordinates. The universe still contains it. It always will. This is the gentlest thing the equations of physics have to offer about loss. It is not a religion. It is not a doctrine. It is what falls out of the math, if you read it carefully, and let it speak. There is one more place this leads. Most of what we have been talking about in this long, quiet documentary is on the scale of the universe. Atoms, planets, moons, black holes, the structure of space-time, the relativity of simultaneity, the block universe, the arrow of time. These are big concepts. They concern the whole of reality. They are by any measure the largest topics that physics has ever taken on. You are not these things. You are not a planet or a moon or a structure of space-time. You are a small body in a small room on a small planet, in a small solar system, in a small spiral arm of a galaxy that is itself only one of perhaps 2 trillion galaxies in the observable universe. You are tiny. Your world line is short. The piece of space-time you occupy is unimaginably small compared to the whole. This is the kind of fact that, if you let it, can make you feel insignificant. It can make you feel like nothing matters, because the universe is so vast and you are so small. This is the standard line, the cliché that gets repeated in introductory astronomy books. The universe is huge. You are tiny. Therefore, you do not matter. But that is not actually what the math says. The math does not have an opinion about what matters. The math is just structure. The structure is enormous. You are a small part of it. Both of these are true. Neither of them by themselves tells you anything about whether you matter, or to whom you matter, or in what way. What I want to suggest instead is something different. The smallness is not a problem. The smallness is part of what holds you. The structure does not care which moment. It does not privilege the moments of large people, or famous people, or important people. It contains the moments of every life equally. The moment you laughed at something quiet in a kitchen when no one else was watching is at its coordinate. The moment you held someone's hand for the last time is at its coordinate. The moment you saw the sky open into a sudden unexpected color at dusk is at its coordinate. None of these moments need to be witnessed by anyone other than you to be real. They are real. They are at their points in the structure. They will always have been. The quietest moments are as permanent as the loudest ones. The unwitnessed afternoons are as fixed as the public triumphs. The small private kindnesses you have offered, the small private fears you have felt, the small private joys you have known, all of these are held by the same geometry that holds the largest stars and the oldest galaxies. There is room for everything. There is room for you. This is, in its way, the kindest thing the equations have to offer. You are not adrift. You are not falling through nothing. You are tracing a small, slow line through a structure that holds you and that has always held you, and that always will. The universe, in its full extent, is a kind of containment. You are inside it. You have always been inside it. You will not, in the deepest sense, ever leave it. So, why does the day have 24 hours? Because Babylonian astronomers 4,000 years ago used a number system based on 60, because 60 divided cleanly into many useful fractions, and they pushed that number up into the sky and divided the sky into 360 degrees and the day into 12 hours of light and 12 hours of darkness. Because Egyptian sundial makers picked up that system and built water clocks around it, because Roman administrators spread it across an empire, because medieval monasteries needed to know when to pray, and the bells preserved the structure for 1,000 years. Because the mechanical clock arrived in the 14th century and turned the hour from a soft, seasonal thing into a fixed quantity. Because railway schedules in the 19th century forced cities to synchronize their clocks. Because an 1884 conference in Washington carved the world into 24 wedges. That is the satisfying answer. You have it now. You can hold it. The honest answer is different. The day does not have 24 hours in any physical sense. The day is a slowly drifting interval, lengthening 1.5 milliseconds per century, as the moon steals the Earth's rotation through the slow, patient friction of the tides. The second is no longer a fraction of a day. The second is a count of vibrations of an atom of cesium-133. The day, as a fundamental piece of reality, is a fiction we have agreed to maintain. And beneath that, the structure of time itself does not behave the way we usually imagine. Time depends on motion. Time depends on gravity. Two clocks in two places do not agree on what time it is. Two observers in two reference frames do not agree on what is happening simultaneously. There is no universal present. There is no shared now. Every observer is on their own timeline. The universe does not have a single tick. And beneath that, in the deepest reading of the equations, all moments exist equally. The past is not gone. The future is not unmade. The flow of time you feel is a local sensation, produced by the increase of entropy as you, a small low-entropy structure, slowly dissolve into the larger sea. The block is whole. Every moment is at its coordinate. Nothing in the structure is ever lost. This is what the equations describe, if you read them carefully. This is what Einstein meant when he wrote, in 1955, 4 weeks before his own death, that the distinction between past, present, and future is an illusion. He was not being poetic. He was reporting what the mathematics of spacetime had revealed to him across 50 years of careful work. The Babylonians could not have known this. The Egyptians could not have known this. The medieval monks ringing their bells, the railway companies setting their schedules, the 1884 delegates dividing the world into time zones. None of them could have known this. The story we have followed, from the cuneiform tablets of Babylon to the cesium atoms in a vacuum chamber, is a story of humans gradually realizing that the thing they were measuring was stranger than they thought, that the day was not what it seemed. That time was not what it seemed, that the universe was, in its quiet structure, something much larger and stranger and more peaceful than the surface suggested. You have followed it all the way through. You have stayed with the question until it stopped being satisfying. You have arrived where the answer leads. Outside, somewhere, the night is moving. The Earth is rotating 1.5 milliseconds per century slower than it used to. The moon is drifting away 1.5 inches per year. The cesium atoms in some laboratory somewhere in the world are oscillating 9 billion times every second, marking out the smallest unit of measured time that we know how to construct. Somewhere a satellite overhead is correcting its clock for the curvature of space-time so that you can find your way to a place you have never been. Somewhere a researcher is wondering whether to abandon leap seconds. Somewhere the structure of the universe extends in 4 dimensions, in every direction, holding every moment of every life that has ever been lived or ever will be lived, all at once, fixed at their coordinates, never erased, never gone. Einstein wrote his letter on March 21st, 1955. He sent it to Geneva. He died on April 18th. By the logic of the block universe, he is still writing it. The pen is still moving. The ink is still drying. The words are still being chosen at the coordinates in space-time that they always occupied and always will occupy. Somewhere in the geometry of reality, he has not yet sent the letter. Somewhere Mikhail Besso has not yet died. Somewhere the 2 old friends are still young, walking together in Zurich, talking about physics, with the long century ahead of them and nothing yet lost. And somewhere you are not yet here. You are not yet watching this. You are not yet falling asleep to a documentary about why the day has 24 hours, with a soft voice walking you slowly through 4,000 years of human attention and the slow, gentle unwinding of what time really is. None of those moments are more real than this one. They are simply elsewhere. Good night.